nice table down there now, huh? Wasn't it up here maybe before? I'm not sure where it was.
It was a talent show.
There was a talent show? Oh, really? Which organization was having a talent show?
Engineering Honors Academy.
All right. Go talent. So Engineering Honors Academy. Huh?
We're pretty talented.
You're pretty talented?
Well, I wasn't.
Okay. All right. Well, good. Good. Well, welcome everybody to class. How's it going? Good? All right. I'm happy to be here with you today to discuss fluid mechanics and the finite volume method. So we're going to transition from finite element to finite volume. And if we go through the different methods that we've been doing in this class, we can reflect on our start with particle dynamics, using Euler method, using the velocity relay method, then progressing to finite difference method, then progressing to finite element method, and now progressing to the finite volume method. Okay. Now, I think the way we've portrayed things at this point is each one of these methods typically gives us some additional capability. This may be and there are also some trade-offs as well, right? In terms of, if you want to simulate particle dynamics, you're not going to use finite difference, or you're not going to use finite difference or finite elements, okay? And today maybe we're not saying so much in connotation that finite volume is better than finite element, which may have been kind of the connotation that I've been portraying as we progress through the class. Today, it's like this is a separate method that is very useful for a class of problems involving fluid mechanics. So that's kind of some context. So before we go, though, into some of the technical content, a few administrative details. One, thank you for submitting your project proposals last Friday. Two, I need to get to them, all right? So that will happen. And if you submitted with a group of two, this is your time before I start sending messages to find that one. If you just want to sit and see what happens, that's fine too. Just saying that we do really want to get to groups of three. The ideal scenario would be that we have all groups of three, and the second optimal solution would be based on the numbers that we have all groups of three and one group of two. Okay, so that's where we are. I've been talking to the TAs some, we're communicating with them, and there are some concerns about some of the assignments that people are submitting. And unfortunately, we are submitting some academic integrity reports. So please, I love it that you're working together. Okay, that's what we want, right? And if and I'm even okay with you having the same exact figure as someone else. That's fine, although it'd be a little bit strange, okay, to do that. All right, but you gotta acknowledge that. What seems to be cropping up is that there's stuff that doesn't necessarily line up with what's in there, and it's identical, and people are submitting multiple things that have identical figures that doesn't necessarily line up with their story. Okay, and that's an issue. Okay, so please do us all a favor, and I'll send out an announcement in Canvas. Right, please do yourselves a favor and us a favor as well. To if you don't know it, the assignments, right? There are so many of them. It's not worth it. Okay, it's not worth it to do something that that we're not supposed to do. Okay. And I understand, right? People you guys are like, well, the faculty, they teach the same thing every semester, right? And I understand. It's like, well, yeah, we try to add a little bit of flair, a little bit of difference. Maybe not flair. Some of us don't have flair. That's giving us too much. So, I mean, I understand that, you're like, oh, well, why don't you all change it up enough? There are slight changes that we've introduced to the problems, like just slight, and hopefully, we can all get along. Any questions or thoughts on this? I'll send out an announcement on, all right? This is very few cases. I just want to make this clear before it gets later in the semester and people get super upset. Okay. And then also, yeah, we expect that for attendance that you will take the image of the attendance thing. All right. So this is not that. All right. And typically, it could happen at any time, but I think you realize that usually happens at the end of class. So just do yourself a favor and don't submit attendance at 2:30, okay, with some random image. All right, the people grading are like, what am I supposed to do here? Well, you can't get full credit, right? That's not the attendance that we're looking for, right? So that's just another thing. Administrative details, just to keep in mind. All right, any questions, any thoughts? I want to be a nice person. I hope I'm a nice person. We also want to be fair, all right, in what we do. Okay? All right, let's get into the fun stuff. Or maybe that was the fun stuff. But we'll get to the real fun stuff. Okay, we're going to talk about mechanics a little bit. Mostly just to have a recollection of the notation and the conventions that we use when we're describing stresses. It's maybe a little bit ironic that we teach mechanics in many curriculums before we teach fluid mechanics. Because in some respects, the equations that are used for simulations in mechanics, as I've mentioned previously, are more complex, and they use the finite element method than, say, some of the partial differential equations that you could solve with the finite difference method, or the finite element method, or the finite volume method. Okay? So, anyway, because we're more familiar with mechanics and fluid mechanics as a co-rec for this course, I thought we'd go back down a very brief, almost animated PowerPoint review of mechanics. If you have any questions on it, you have the slides. Maybe it's not the best form of teaching, just to kind of put it, and we're just trying to get jogger memories about the notations that we use for stresses. Okay. Then we'll go into fluid mechanics, and some of this should be a review, I think, by this point. Well, I don't know, we'll see. We'll have some interactive moments, maybe some pauses as I look at you longingly for answers. Okay, that's okay. But hopefully you get some insights that we can then take into our understanding for doing simulations. Because after all, there are two reasons to understand fluid mechanics. At least two, to understand the basics of fluid mechanics before you start simulating fluid mechanics. One is baby steps, right? So we talked about this in terms of convergence, comparison to some ground truth, right? So if you have a fluid mechanics problem that you know the answer to, and you put it in, solves it correctly, sounds good, right? That's one reason. Two is just to interpret what the answers, what the simulation is telling you, right? So if there are going to be things that, of course, I don't expect us to understand, that the ANSYS or any finite element software package will spit out. There are all kinds of interesting terms and things that you can have it spit out. Nonetheless, kind of the basics we want to understand. Like, we want to understand that, hey, we really care, mostly in fluid simulations, we care a lot about the velocity profiles, right? And then we care a lot about drag. So we're going to care about forces. We're going to care about the shear stresses or the normal stresses that are involved on surface that create forces that would be the lift and the drag, right, on an object. So just kind of trying to connect some of these dots is what we're trying to do. Okay? Trying. And then the finite volume method, which is very powerful and when used appropriately. So here we go, mechanics. How do you define stress? I mean, you can look, but in your own words, what is stress? Okay, some type of force divided by area. Good. Okay, that gives us the units for sure. Okay, what else? What else can we say about, like, what is it physically? What is a stress? Yes, is it Rishi?
Yeah.
Okay, and it's Johnny. Okay, yes.
Like in real life, you can't really take a solution and measure a force on it. Really sort of approximate. So it's better to like take the area and then take the force that's on that whole area and then you come out stress.
Yeah, yeah. So you're getting to this idea of, okay, maybe you have like a material element or fluid element, right? And it could be infinitesimally small, right? And it could be at some given location. And we are trying to understand what the internal forces at that location are doing and how they're distributed over that material element. Okay, that's kind of, I think, what you're saying, right? So, we in mechanics and materials, we took lots of slices, right? And normally that's pretty good because you take a slice through to the object and we're like, for our intents and purposes, the stresses are uniform across whatever face we're dealing with. In reality, and as you get to more complex problems, you know that you have stress concentrations, you know that you have gradients in the stresses, and it's not just, all hunky-dory the same on every slice you take. And then you also know that, okay, depending on the slice I take, I do expect to see different profiles. So we're interested in having a almost a language that we can communicate how materials, how fluids, how systems are experiencing mechanical load. And so you remember that we have maybe some type of internal surface in a body or two, or maybe they're interfacing, whatever they are, and then we have some type of traction, force traction vector, and then we split it up into these small dAs, right, and you get force divided by area, right? So this is kind of just a review, and you can go back, and these slides, of course, are available, both in this course and also, when we took mechanics. If you took mechanics and materials, when you have them, and if not, you can ask your buddies for where they are. So again, we have like this traction vector, this small force, and then we are describing it and shrinking down the area over which it's acting, and then we have the ability to then put this into components in the I, J, and K directions, and we can think of the stresses as a quotient of these small forces acting over these small areas. Okay? Sound familiar? How many of you have been dealing with these types of stresses on a regular basis now, since you took mechanics and materials? Yes, where are you seeing them?
Other classes.
In other classes? All right, so what are the other classes? Like, are you taking DMC right now? Yeah, right? So, all over the place, right? If you thought it was tricky in mechanics and materials, now at least you have tables that tell you what to do, right? So it's kind of nice. But, yeah. Other places? Do any of you have X-ray vision? I wish I had better X-ray vision. Like, look at a structure and like, hey, the stresses are high on these parts, right? Like, oh, that's a bending moment across that plate or that thing. That's what they probably look like. I know where this is going to break. I have an idea. Okay? This is because we have high stresses, right? So that's kind of one of the things we're trying to develop develop our intuition for what's going on. Okay. And of course we love the normal stresses. Well, not because I'm a normal person, but because it's kind of simple to have the aerial vector going in the same direction as the force vector, and you can kind of pull something apart, and it's a little bit, intuitive. But of course, we have these other stresses, which are the shear stresses, and that's when you have a subscript for the face. Right? Remember here, right? The first subscript is going to be the face on which you're acting, or the normal vector coming out of that. Not dissimilar from what we discussed when we were looking at bouncing balls off of walls. And the second subscript is going to be the direction of our stress. So when I and j are like the same number, right, or the same letter, x, y, or z, then we have a normal stress. And when they're different, that's going to be a shear stress. So, yes, and these are indices, they're not the directions, the hats of the directions. Okay? And that's also kind of important to keep in mind, right? And, you know, I remember talking to another very, well, not another, a very wise professor, I respect. He loved or told me this story that at the end of their class in fluid mechanics, he was in grad class, actually. One of the students approached this professor and said, hey, why don't we write sigma subscript I, j, k, right? 3 dimensions. What do you think this fluid professor's reaction was? Yes?
Is it because you have to do like X, Y, like do you need like 2 of those things?
Right. What are you going to do with the third one? Right? You're already working in 3 dimensions because I and j, those, not the I hat, j hat, k hat, right? The I and j, those are indices reflecting dimensions 1, 2, and 3. Right? So, I personally think that this teacher was probably doing an excellent job. Okay, my guess. Nonetheless, I have questions that get asked of me at the end of the semester, and I'm like, what did I do? Where was I? What was I doing? So, yes, if you go into a job interview, don't say, oh yeah, I know a lot about stress, right? Sigma ijk. Please don't do that. Okay. Anyway, so the normal stress again, we have the same subscript letters or numbers, right? We talked about the Cauchy stress tensor, which is sometimes given by the sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1. Okay, I don't have to go through all of them, but you get the idea, right? You can use numbers instead of letters. Again, we're just kind of reviewing this and going through these things really quickly so that we can get to fluid mechanics. Okay? And in mechanics, we have equilibrium that we have to solve or satisfy. And we can go through this and figure these things out just like that. Turns out that shear stress is often a little bit more relevant to fluid mechanics than normal stresses. So, just, you know, as you think about what's happening on a material element, remember that you have to put arrows on all 4 faces of a 2D element. Right? So you're going to need to have satisfaction and equilibrium, whether it's a material that's like solid or even a shear stress. Or even a fluid element. Okay. All right, so any questions, any insights, anything you want to emphasize when we're talking about stresses in mechanics? We already talked about tensors, and the beautiful thing about tensors is that you can rotate them and the information stays the same. And if you watch that video way back maybe last year, what the heck is a tensor? I think that YouTube does a pretty good job of explaining. Okay, anything, any comments, hopes? What was your favorite geometry or your favorite type of stress to calculate for mechanical materials? Yes? Principal stress. Okay, what was like a specific example where you calculated a principal stress that you were really happy about? All of them? That's pretty vague. Pretty vague. So when were you calculating principal stresses? What's the difference between a principal stress and a normal stress? Yes, and what happens to all the shear stresses? They go to 0, right? And what's the tool that you usually use to get your principal stresses? Or a circle, right? Okay, good. Yeah. So I'm putting words into your mouth, but I'm guessing you really like covering more circle. That was one of your favorite topics? No. Yes? Okay. No? Okay. Well, that's okay. How many of you actually use more circle instead of like using that transformation equation? All right, that's good, all right, that's good. Okay. All right, that's, more circle is something that could actually come up in the job interview, I think. That's like fair game. I didn't, I had a mechanics question come up, but it was the flexure formula, sigma equals negative my over I, so they wanted me to calculate the bending stress. So that, but they could do more circles. All right. Take a look, read and digest, and in English, there is English on this, okay, but in your own words, what does the geometry I want you all to describe what this geometry means. What's going on here? In your, okay, that was fast. Go ahead, tell me what's going on.
There's flowing through like a pipe or something, and because it's perpendicular, like parallel to the actual walls, it's like a shear stress instead of any other like normal stress, because they're sort of like, I guess, like shredding on each other. If that makes sense.
Okay, that's kind of clear. So you wanna clarify what is causing? Let's start with what do you think is causing the flow? You're right. There is flow, but what's causing the flow here? Huh?
Velocity.
Okay, that's kind of synonymous. I want a little more detail. Like, yeah, flow, velocity. There is flow. If there's velocity of the fluid, there's flow. True. But I want like what is causing the flow? Yes. That's right, okay? The top plate is moving to the right. The bottom plate is stationary. What's your name? John. Okay. So John, what is the velocity profile across this gap? Right. So you see which line on there is describing that slope? Yeah. Well, okay. So I guess maybe the colors are not super clear. Can we say it's this one? Okay. Right. And this is the velocity v naught of the top plate, correct? Good. Very good. Now, I've done something kind of strange here. I drew a shear stress that's constant. Why? Is it? It might not be the clearest depiction, but I tried to make them both light blue. All right, so what I'm trying to say is that the shear stress is constant at any y. What's going on? Yes?
In the equation, tau equals dp dy. We know that viscosity has to stay constant. So it could be because the velocity and the position in the y is like proportional. So I guess one increases, the other one decreases.
Yeah. Okay. All right. Yeah. All right. So, have any of you ever tried to measure viscosity? No. Okay. What is an example of a like? Do you have a context? I have some idea. Like for liquids now, we're talking about liquids, and fluids, right, encompasses gases as well, right? But we're talking about liquids, right? State of matter liquids. What are some of the least viscous fluids that you can imagine? And what are some of the more viscous, or most viscous liquids that you can imagine? Okay, water and honey. Okay, what were you going to say? Something in the back? Okay, so oil is all over the place, right? And we'll talk about oils in a minute, all right? Water and honey, okay, so water, and then essentially water plus some type of sugar, all right, becomes very viscous. orders of magnitude, right? It's not just electrical engineers that can say, oh, I have a 1 ohm resistor, right? And I have a 1 mega ohm resistor. Viscosity is actually something where we do have multiple orders of magnitude. Okay? And you're like, it's not that really, it doesn't feel that different. Water is really got a low viscosity. Okay, it is a pretty low viscosity, you know, 1 millipascal second, and a lot of the oils, they start at the viscosity of water and they move up. How do the oils change their viscosity? What is the viscosity of an oil dependent on? I mean, it's dependent on chemical composition, but also there's one other thing that it's usually dependent on. Any idea? Yes.
Temperature?
Okay, temperature, yes. Temperature makes a big difference. Yes. Good. What else? And so obviously, but at lower temperatures, when you're turning your car on, an internal combustion engine car, that is. Okay. At low temperatures, what's going on? The viscosity is pretty high, right? So it's got to do a little bit more work to get going. Right, and then it warms up, viscosity goes down, and then you have your different SAE 5, whatever, 10, 10, whatever those are, right? So there are all kinds of different grades for temperatures and everything. What kind of chemically, what determines the viscosity of an oil? Yes.
How strong the bonds are?
Okay, we're getting very, very close. Yes. It's a spaghetti problem. Okay. For many oils, it's about their polymer length, how long their polymer chains are. Okay. So you have like silicones that will have different chain lengths. The longer they are, typically the more viscosity that particular silicone oil is going to have. So, very, very, very good. All right. So now let's go back to this problem. And I guess, what are the boundary conditions here? We should probably say what they are, right? Just here, right? What are the boundary conditions?
So that the bottom.
Yeah, and
Moving in beyond.
which means that there's also no slip, right? So there's no slip at the bottom and the top. And what does no slip mean? Kind of, not exactly, John. Okay, what's up? Your name again is, I always forget it. Huh? Anthony, yes. What were you going to say, Anthony? No. No, that's an interesting idea, but let's think about it. What's going on? It's a very simple thing. What does no slip mean? If I'm on an escalator, or I'm sorry, conveyor belt, and I'm not slipping, what does that mean? Anthony, go ahead. What does it mean?
You're moving with it. So.
Exactly. The particles are moving at the same speed as the wall. Okay? So if the conveyor belt is moving, those particles, and I'm a solid. It's going to move, right, as the conveyor belt moves. So if the walls are fixed, then yes, you're going to have a gradient there, okay? And you're going to have essentially very close to zero velocity, essentially zero velocity, right at the wall edge, and then it goes up. Or it goes, or the surrounding flow influences. Right? So that's what no slip means. Now, here is another opportunity to solve a kind of algebra or calculus problem, fluid mechanics problem. We have the boundary conditions described here, both with with the no slip condition in place. Okay? And we have V naught as the velocity at the top, and 0 as the velocity at the bottom. And we're going to say it's a thin gap, so that means that we can have essentially a linear approximation for what the particle velocity is going to be as we go from y equals 0 all the way to y equals h. And the gradient of this velocity is this du dy. Okay, that's when we say u is going to be, well, we already said the fluid velocity u of y. And so the gradient is going to be the derivative with respect to y. And that means that we're just going to have this v naught divided by h. So what is the shear stress based on the stuff on the left? Yeah?
Mu v naught over h.
Right. Mu v naught over h, and that's why the tau, that blue light blue tau there, it's constant. Alright, so that's the shear stress is what we're depicting there. So it's going to be the same across. So now let's go back to that question. What is a good way to measure the viscosity of a liquid? Or what is one way to do it? Yes, Rishi?
Find the velocities at the top and the bottom so that you can look at the dy. And if you know the shear stress, then solve for viscosity.
Okay, so how do I calculate shear stress? It's somewhat of a trick question, and I haven't given you all the information.
Do you do the F drag equals CV, like CV squared?
Okay, so yeah, I mean that's like you're talking about the drag force and calculating the drag the coefficient of drag by saying, hey, 1/2 rho CV, that's the drag coefficient times the velocity squared. Okay, yeah, not here. We're not. That's a little. I mean, that's a little complicated for what we're trying to do, and it doesn't quite get us immediately to the viscosity of the liquid. All right. How do you calculate? How do I do an experiment with what I've just said right now? And there's one piece of information I haven't shared with you. You have to make one more lead. Okay, but how would you go about using some type of setup like this to calculate the viscosity of the liquid? I mentioned that we might have some silence. It's not that awkward. You are very, very smart people. Come on. I didn't tell you it. I didn't give you the last piece of information. Yes, okay. No, not pressure times velocity. No. Well, you're getting. I can just kind of see where you're going because, like, yeah, we love PV and we love all kinds of stuff, but no. And those are even different PVs. Anyway, but yeah, no. But you're close. What do we know how to calculate at this point? Well, if I know the velocity, right? I know the thickness, I can calculate what du dy is. Right? But I don't know how to but if I don't have you want to find the viscosity, right? So like, okay, mu times du dy, that's great, but I don't know what mu is. Right? But how could I find out what mu is? based on the equation on the left. Yes, Rohan.
Can you use the shear stress?
Okay, so how do I calculate? So yeah, so if I knew the shear stress, I knew the gradient, then I can figure out the viscosity, right? So how do I figure out the shear stress? Yeah, no, yes, happy but not happy. Okay.
Well, I mean, I was gonna say something else. Be different. I don't know how you would find the shear stress, but now I know what I.
Okay, all right. So tell me. Yes.
Can we use something from like mechanics and materials?
Oh, yeah, because we just talked about mechanics and materials. Okay, so what is that something?
Can we measure some kind of strain?
Okay, I mean, yeah, but that kind of like, then I need like essentially, I need some type of shear modulus, right? Which kind of is, so you're really close. You're really close. How can I calculate the shear stress? Using what we know in the mechanics of materials. Yes, Rohan?
Use more circles.
No, come on! More circles not the answer for everything. That's okay, though. I like it. Come on, you gotta have the concrete. Yes. That was great, Rohan. All right. What do you think? Yes, we should.
Is it accelerated?
No, steady state. Yes.
Is it just gonna be the weight of like the fluid at like a particular point over an area?
We're getting close. Not the weight over a particular area.
Force of the weight.
It is a force over an area. I agree.
Something like flux or something.
No. What force might you measure? Yeah.
Can we use like the momentum of the fluid?
I mean, it's no. Let's not. No. Yes.
It's the drag force
Of.
of the fluid onto the surface.
Okay. And how do I measure that force? Okay, we're using double jargon. I'm an experimentalist. I just want to know. Tell me what to measure. And where to measure it.
Change of velocity.
No. We already got the velocity. We know that. Yes. Oh, come on. No. Where are we measuring the force?
One of the surfaces.
Yes. In which direction?
Parallel to.
Yes. So what do? You take a little force gauge, or you can make this a vertical setup, whatever you want to do, and you measure how much force you have to pull that top plate with relative to the bottom plate. That's it. All right? So if you go home, and I hope you wash your hands before you go to bed at some point, right? And you take your two hands and you put a little water in between them. You go like that. Like, 0.01 or 0.01 Pascal second. So it's a 1 millipascal second. That's what it feels like. That's like the viscosity. Sorry, I can't remember the viscosity of water. I'm kind of embarrassed. Okay, I'm sorry. Sorry, that's really it's unacceptable. I'll have to make it up to you at some point. It slipped my mind. Anyway, so, and then take a little soap. Alright? And then put some soap in between your fingers and that water. And you move. And you're like, wow, that is less force. Alright? There you go. You've got your rheometer. Okay? Your hands. So this is actually how they do it. They take, you take two plates, and usually they're spinning discs, actually. Okay? And there's some that they go in the same direction, all right, all the time. And there's some that they're oscillating geometry. Okay? And so it goes back and forth, or it goes, and back and forth is good when you have like a solid, like a viscoelastic material, solid liquid type of thing. Because if you keep going in the same direction on a solid, guess what happens? You break the solid. So like this, or you go like, anyway, and so that's how you calculate it. Of course, the velocity is not the same through those plates, right? It starts at 0 in the middle and then it goes out and it's higher. But you can integrate it and figure it out. So why do we talk about the mechanics and materials business? Because essentially you have a shear stress on a surface and you integrate that over the area of the surface, and that's how you calculate the fluid. Okay. Why is this relevant to what we do in simulations? Why are we bringing this up? Why am I bringing it up? Why would I want to know the force acting on a surface? And that's where you can say, well, because I want to calculate the coefficient of drag, or I want to calculate the coefficient of lift. Right? I could have a normal surface, right, or a normal force, or I could have components of normal and shear, right, on surfaces and try to figure out, okay, that's contributing to drag, that's contributing to lift. Okay? So at its heart, this type of simple problem helps us understand what we're doing when we do certain types of fluid structure interactions, okay, in simulation. All right. So, yeah, this is just what the viscosity is. All right. Now, the fluid element is experiencing shear stress. And I think it's also good to remind us, and we just showed this a minute ago, that if you have a shear stress on one side, okay, like that, you have a corresponding shear stress on the other side, and this fluid element still is in equilibrium with the small element. So that you're going to have these other arrows for shear stress. So the fluid is being distorted. It's right. You've heard shear, right? You know shear. So that's what we're dealing with. Now, that was kind of like the basic 2D problem with flow in one direction, where plates, and because you had X and Y, you had a gap, and you had flow in one direction. But you could also have flow in two directions, right? You could have flow going this direction, you could have flow going this direction, you could actually have flow in that direction, but that would be kind of not fun. So what you have are opportunities to think about these shear stresses that develop from multiple flows in multiple directions through multiple gaps. And they can both contribute to the shear stress in a given direction. So typically, so this is like for a 2D incompressible flow. In that case, it would be thinking about kind of what's happening in the vertical direction as a function of x, in addition to the horizontal direction as a function of y. Okay? And you add them together as you see here. And these partial derivatives are what you use to get the shear stress. And if we go to 3D now, we have this representation of, okay, there are two flows in two directions that are going to contribute to the shear stress in that plane. So like the XY plane, the YZ plane, the XZ plane. Okay? And we have all these partial derivatives, right? These, the ones where you have the flow in the same direction as the direction, not going to contribute shear, right? So the main diagonal is not going to be contributing shear. But the off-diagonal terms, just like in mechanics, those are the ones that contribute to the shear stress. And you can write it in this compact tensor notation at the bottom. Now, like you see here. When you do simulations, you can have it calculate shear stresses, you can have it calculate normal stresses. Normal stresses are going to be in the form of kind of your hydrostatic pressures. Okay. But you can have it calculate shear stresses. But often we care more about flows, and we do care about the integration of these shear stresses or normal stresses on surfaces so that we can calculate drag. So, anyone watch The Efficient Engineer? No? Yeah? Which class do you think it helped you with? Yeah, I think it helps with mechanics materials. I think it helps with fluid mechanics. think it helps with a lot of things. Heat transfer, right? I don't know, it's like the organic chemistry tutor, right? We don't know who they are by appearance, but boy, they're doing some nice work for us. Okay. No one's watched The Efficient Engineer? All right, if you haven't watched The Efficient Engineer and you're bored on a Friday night, watch The Efficient Engineer. It's more exciting than watching these videos on a Friday night. Okay? So, that was about viscosity. So, for those of you who have taken fluids or in fluids, what are your feelings towards the Reynolds number? Yeah? Okay, why do you like the Reynolds number, Anthony? You like it? Okay. This is like the most important dimensionless number a mechanical engineer can use, probably. What about you?
I was gonna say it gives me information on if it's Laminar or Turbulent.
Okay, yeah, exactly, right? And Reynolds numbers are kind of funny because it depends on the geometry and the situation that you're using. So, like, sometimes turbulent flow has to be like hundreds of thousands, but then in other cases it's like, oh, it's just if it's above 600, it's turbulent, right? So it just depends a little bit on the geometry and the conditions that you're using. So, like, you'll see really large Reynolds numbers when you have very low viscosity. So for a lot of the aerodynamic flows, right, you're going to have, when you have air, you're going to have a small mu, so that's going to jack up the Reynolds number pretty quickly. And then there are other situations where you're doing stuff in like microfluidics or small chambers with water, which has a pretty small viscosity, and you're talking, if you're in the hundreds or thousands, that's pretty turbulent, right? Like in pipes, 2400 was one of those numbers that you kind of care about. So the Reynolds number does tell us whether something, gives us a clue of whether or not something's going to be turbulent or laminar in its flow. And what is it? Ultimately a ratio? Balancing? Does it say it here very succinctly? It should.
Like the body force and stuff. Is it like viscous?
Yes. Yes. So, yeah.
Is it the inertial force and the viscous force?
Right, so you have rho v over mu, right? And so rho and v give you some idea of what's going on with the inertia. And then viscosity, right, is in the denominator. So yeah, it's a nice balance between the inertial forces in the system. And so here you go. That's the equation, and we'll be talking about Reynolds number quite a bit as we do. Now, if you're bored on a Friday night and your professor says, please derive the Navier-Stokes equations, you can remember this. If you don't care about this, you can go take a sleep. Alright? But we're just going to go through Navier-Stokes, how it comes to be. And we're going to use the conservation of momentum, conservation of mass, and try to solve this. Okay? So we have an equilibrium. So if we have a velocity field in 3D space, in Cartesian coordinates, as a function of time, this is one way to write that. Okay, so now you've got this u for the velocity in the x direction, v for the velocity in the j or y direction, and w for the velocity. And actually, when you look at it, it's like, hey, that's not that complicated. Okay, acceleration, you take a derivative of it with respect to time. And this is a dv dt. And it is something that we can represent in terms of partial derivatives. Okay, so this is not, this expression has no partial derivatives in it. It's talk about that in a little bit. But this is just a derivative. So then the chain rule can be applied as such. Okay? This is saying, take a look at one of the derivatives, the du dt, and then bring it over here, and let's use the chain rule, and we're going to introduce some partials. So there's going to be some dependence on the time that we can cover here. There's still dependence on the time over here. Okay, there's time dependence over here, time dependence over here, and we can multiply by these partials like you see there. And this is just the u, this is the v, this is the w, which comes out of here, here, and here. And then now we have a new way of writing each one of these components. And we can write out this divergence operator, okay, or the v dotted with the gradient operator, as we see here. And times the u. So this is just getting us back to this partial expression, which is just the right half of this right-hand expression. So you still have the partial of u over here, and you have these three terms here. Now, when we copy and paste this, right, we can say, all right, the acceleration can be rewritten as this. Okay, so you see this is just like acceleration in what? In the x direction. So that's what you have here, but I can substitute in the velocity vector instead and put it in where we have the little u. And so this is the acceleration written in another kind of succinct but complicated form. And if we have steady flow, right, then we can say that the time dependence goes away. But what we have over here is a velocity field that is dependent completely, well, this part right here, it's dependent completely on space. So this is going to be pronounced in a situation where you've got some type of object that is flowing over it. Maybe it's a nozzle, maybe it's an airflow. When you think about whether or not you're solving a steady state problem, you say, oh, immediately, well, if you set the derivative of this thing, we get rid of the time components and everything, that's what we're interested in. When you were solving the turkey problem, was that a steady state solution? No, right? Because what? Why? Because we were just getting to a specific time, and we know that the temperature profile across the turkey was still changing, right? In the oven, what does a steady state solution look like for that turkey? Yeah, Anthony? Okay, yeah, and were you going to say something, Isha? Yeah, the entire turkey is the same temperature, right? It's ultra cooked, probably, and dry, and all the same temperature. Okay. So, that problem wasn't very interesting in the sense of the thermal profile across the turkey. So I didn't focus on it. But are there thermal problems where it's very interesting to have a steady state solution? Of course, and we've talked about this a little bit, right? If I got some type of heat flux on one side of a wall and some type of heat sink inside, or vice versa, whatever it might be, right? But I can have steady state profiles of temperature across the thing, right? Like I'm walking around and I'm in an environment that's more or less at a constant temperature. I've been standing here moving around a little bit, maybe I'm like, I don't know, watts overall. Okay. And so there's probably a nice little thermal gradient through my clothes, right? So that's an example of a steady state type of problem that is interesting. That's still a thermal problem. What are the interesting steady state problems in fluid mechanics? Or some of them, not all. But what are steady state problems that are interesting in fluid mechanics? Someone from quadrant 2. Quadrants 1 and 3 and 4 have been active. Quadrant 2. What is an interesting steady state problem in fluid mechanics? Or what is an example, maybe not interesting, what is any example of a steady state fluid problem in fluid mechanics? Yes? Okay, yeah, and what's the condition there? What have we established? If it's a steady state, what have we established? Okay, all right. Well, there can still be that there's no acceleration, right? So you get in your car and you're on the highway and you're not driving like most New Jersey drivers, right? Where you're going, right? You're just like cruising, just chill. You hit the cruise control, right? And I want to figure out how much fuel am I spending. If I were in a vacuum, right, would I have to continue to push the accelerator? No, right? Because there would be no wind resistance. Okay? But because I'm not, and if I were going flat, right, all these other conditions. So that's an example where we might be interested in doing a simulation and looking at the steady state answer because planes cruise more or less at a constant speed. Cars cruise at a constant speed. And so we can get some ideas of comparisons for how they're cutting through the surrounding media and how fuel efficient they might be. All right, so anyway, so this comes down to we might be interested in looking at steady state problems where the partial of v with respect to t is 0. Okay. Not so much the partial of x with respect to t, right? Or like u and v and w aren't necessarily 0. That's not the requirement for steady state, right? What is required is that the derivative of the velocity is equal to 0. All right, so this d dt, this is not a partial, okay? It's something that's often referred to as the total derivative or the material derivative. And it can have a few terms. It can have these 4 terms. Okay, so the 4 terms, well, let's go back. We've kind of seen it, right? We can have these 4 terms that come out with the chain rule, just like that, okay? Now, control volumes. And these will keep you up on Friday night. Let's say that you have some type of square, some type of element, and we have something going in and something coming out, and it's just a small gap that we've covered, okay? And it's in the x direction, so we can think of, okay, there's some type of change that's related to the x direction, okay? Like you see there. We can also write these equations in the xz and xy planes. This one is in the xy plane, boom, boom, right? And this ends up being kind of a description of a differential depiction of mass conservation. Okay, and then there's also the integral form of mass conservation. So in this case, you know, if the volume itself is somehow generating volume, right, or changing that volume, that's something we can consider. But often, you're looking at the input of mass and its rate of such is going to be equal to the output of mass. Okay, so that's mass conservation. what we can, and it's 2D, right? We can kind of get rid of some of these terms. We can cross them all out, 2D or 3D, whatever it is, and we can get this simplified equation, and then this equation is what you might see to describe mass conservation. And if the density is not changing, then what you'll see for an incompressible fluid is that it's just the gradient dotted with rho v. So here we have the divergence. Okay, so this gradient dotted of rho v, the divergence, okay, of the density times v is equal to 0. Oops, wrong way. And if you go through this, like I just said, for an incompressible, then you just end up with the divergence of velocity. So we can use this conservation of mass. We can think about it in the context of incompressible fluids, as we've already done here. And we can also begin to think about these fluxes as they go through these control surfaces. And we already showed the integral form of this. Now, momentum, okay, we can also think of as being the stresses, right, acting on these surfaces and then having to balance out in terms of the forces that they create. So stress is acting on surface areas, okay, and then balancing them out. And when you do that, you get a little bit more math, and finally, and when you balance this out, the hydrostatic and the viscous and shear stresses, you do this all out, and you can get what we call the Navier-Stokes equation, like you see here. This is the gravity term, this is the hydrostatic term, and this is the shear term, and this is the inertia term. So what's cool is that you don't have to solve this manually like you did before. Well, actually you do, right? You do some cases of fluid mechanics where they give you the boundary conditions, like the first problem we said, right? Say, hey, you know, what's the, you got the velocity here, you got the velocity here. Tell me what the profile is for the velocity through this pipe or between these plates might be, and use Navier-Stokes to do so. Okay? But what we're going to use is the finite volume method to solve Navier-Stokes equations. So here is a nice picture that describes what we've been doing in some respects. We've been taking physical problems with physical domains. We've been modeling them. We've been coming up with the differential equations that guide the physics. And then we've been doing discretization, right? And initially we were just discretizing in time. But now we're also and then we started discretizing in space as well. And we're still doing that. We have finite difference, finite element, and now finite volume that discretizes in space and time. The goal is to get a bunch of algebraic equations that we can then solve. Right? Remember we talked about this? You've got to get this K matrix and you get it inverted. And then you multiply it times the forcing function, and then you get whatever you're interested in. Maybe it's temperatures. That's kind of the root. That's kind of what we do. So in the finite volume method, what we do is we discretize. Well, first you set up. I like what they do here in this book / article. Is that you take your problem, and in this case, here's a heat source. It's the microprocessor. There's some type of geometry, and then there's some heat sink. So maybe this is the microprocessor, and where is it? What's causing the heat in the microprocessor? Yeah, go ahead, Anthony. Right, that's called joule heating, right? Yeah, so you got some current, you got some resistance, you got some voltage, right? So you've got volt VI essentially, current And then maybe this is like some type of conductive material, like copper or something, that takes you to a heat sink. And what's the heat sink doing? It's sucking out the heat, maybe through some type of fin structure or something. Or maybe there's water cooling, whatever it is, but that's where the heat is going. So then the physical model looks very similar to it, where we have some boundary conditions that have been imposed. We have a heat equation, all right, combination of what we talked about a few times ago with conduction and Fourier's law. Then we get the heat equation, and then we discretize the domain, and then we have equations that we can work to solve, and here's the matrix that gets inverted. Okay, so that's the basic. Remember, we're just kind of doing the impressionist perspective here. But let's go a little bit more into the paint. Here is a steady-state heat equation. We're assuming this is an example of what we're trying to do. We invert this gradient, this Laplacian operator, as you see here at the top in the purple. Okay, right? We said, hey, look, if I get this equation right here, and then I can invert it, then I can solve for the temperature profile. Okay, so that's what we're trying to do. We're trying to solve for the temperature profile. And as you saw, remember with the finite difference method, it was usually easier to think about what's going on in the middle rather than at the boundaries, right? The central difference. So here, we're looking at element number 9. Okay, and element number 9 has 4 boundaries, 4 walls. And this is the same heat equation, right? Same heat equation. But what have we done? We've done a volume integral on that box. And it's a little bit weird, right? But you're like, oh, I can kind of see that. Now I've got this heat flux, right? That might have been generated or, been, like maybe there's a laser focus right on that box, right? Or maybe there's some kind of heat source there. Especially if it's the processor, right? The processor is patch number 3 over here, right? But, whatever, the internal heat flux. And then you've got some interesting behavior happening with this volume integral on the minus a Laplacian of t. Well, to handle that left side, people have gone back to the divergence theorem. And maybe you remember it from your days in multivariable calculus. Maybe you don't want to remember it. But essentially, it's this theorem that says, hey, if you're taking a volume integral, you can re-evaluate it thinking about it as an integral on the surrounding surfaces. Okay? So this component over here gets converted over to this component right here, dotted with ds. Okay? And on the right side, we're not using the divergence theorem. We're just saying integrate dv. It becomes a volume, the volume of the control volume, and it's just multiplied by q dot. And then now that you have this surface integral, you can think of it as, okay, it's going to be some integral, and you've got 4 discrete surfaces that you can think of as a Riemann sum, and dotted with the appropriate surface vectors is equal to this. And that's the finite volume method, pretty much. Okay, so the finite volume method says solve or create the equation for this element as you see it here with the 4 faces, F1, F2, F3, F4, okay? And what are SF1? Well, it's just what is the, for this one, right, over here, this is F, this one we're calling F1, okay? Sorry, that's F3, this is F1. F1 is just a delta Y, and yeah, it can go in some, maybe has a Z direction as well, but it's just this length, okay, which is a small length, times the I. That's the x direction, I hat. Okay? And you do this on all four sides. And we sum the fluxes at the centroids of the faces. Now, what do you all think? Is this simpler than the finite element method? In terms of the math. What did the finite element method have that was really interestingly tricky? Remember those test trial basis functions? And like it had like, you had to have that weak condition? Okay, we don't have any of that. So this is really a nice, simple technique. Okay? And essentially you come up, you had to do some finite difference here, as you see, but that's it. You've got the delta t, the minus k times it, and you solve for these fluxes on all four sides, and you set up your k matrix and you invert it. That's it. So this is a very simple technique, and it turns out it's very powerful and it conserves volume. Imagine that, right? That's kind of at its crux. So it allows us to represent, like there's here, right? We have the volume of the box, right? And it's a thermal problem. We like the heat equation because what? Because it's a pretty simple second order partial differential equation that needs solving. It turns out that this finite volume method also is very good for fluids and flows. So there is some friendly competition, I guess you could say, between this method and the finite element method. Some parties will say, all I need is finite elements. All right? Like all you need is love, all you need is finite element. Right? And that's what COMSOL is saying. What does ANSYS do? Well, it allows us to use finite elements like we were doing for thermal problems, and it also has another package that it bought on Fluent. And Fluent uses the finite volume. Now, COMSOL is all in. So COMSOL is like, just give me finite elements. That's all you need. Okay? Nonetheless, they will even acknowledge that the finite volume method is good for heat transfer. So we're there. Also for computational fluid dynamics and chemical engineering, which often has chemical reactions with those two other elements, right? You have to have heat transfer and you have to have fluid flow. So Fluent can be really fast for problems that will give finite element more of a headache. But finite element arguably is a little bit more universal, and the equations can be set up, and we have basis functions that we can use that will accommodate different types of physics. All right, so that's pretty much what we have for today. Any questions, any insights? You've got a little bit more perspective now, I hope, on the finite volume method. When you're doing different things in the lab, you'll be able to kind of say, oh yeah, I've got these heat fluxes that are solved for, or I've got this kind of fun problem that I'm solving for. All right? And I can do some, you're going to be doing some flow in a pipe. Let's go ahead and take attendance. All right, but any other questions, any other thoughts, comments, criticisms? I've had a request to kind of post a MATLAB documentation website. So we still do a decent amount of MATLAB, and if you're not sure about what any of the functions that we're using might be in MATLAB, take a look. Or go into the command window and type help. I think I've said it before. Help that function. And it will give you a good synopsis of what's going on. So anyway, so that's like a side topic. But let's go ahead and do attendance. Thank you for being here today.